In this video, we will consider this equation where a is greater than 0 and k is negative. Our goal is to find the number of real roots which this equation has at different values of parameters a and k. Why at all this problem is important? Let us consider an example. Suppose we need to solve equation 3 to power x equal 9 over 2x. The simple inspection shows that this equation has a root x equal 2. Indeed, at x equal 2, left-hand side equal 9, and right-hand side of this equation also equal 9. So this is a root, and we can think that we solve the problem. However, if we plot the left-hand side and right-hand side of this equation, we will see that these two curves intersect in 2 points. One of them corresponds to x equal 2. In our case, it's x1. And the second one corresponds to other value, which approximately equal 0.31. And indeed, if you plug in this number into equation, you will see that this is approximately the root of this equation. So without this analysis, we would miss the additional root of the equation, so the problem would not be solved. Now we return to our problem and explain why we selected the case k is negative. This is because the case of positive k was considered previously, and the link to that video you can find in the description to this video. Solving our problem, we will rewrite this equation. First, we will replace k in this form as negative absolute value of k. We plug in to the right hand side and we will get our equation in this form. Then we mention that left hand side of the equation is positive. For this reason, right hand side is also positive, and from here we conclude that x should be negative. Next, we introduce new variable z given by this equation, and because x is negative, z is positive. Next, we can find x from here, and we can replace right hand side of our equation with z, and then plug in x to the left hand side. As a result, we will have equation for z in this form. As a next step, we take a logarithm of both parts of this equation, and we will use the property of logarithm and move this exponent as a multiplier. Then we divide both parts over z, and we will have equation in this form. Right hand side is a constant. We replace it with a new constant b, plug in b here, and we will have equation for z in very simple form. The number of real roots of this equation is equal to the number of real roots of our initial equation. At this point, we mention that equation of this type was solved previously, and the link to this solution one can find in the description to this video. The answer is formulated in the form of diagram, from which we see that the number of real roots varies from 0, no roots, to 2 roots, an interval of b from 0 to 1 over e, and there are also the region for single solution, b less than 0, and specific solution at b equal 1 over e. We will use this to solve our problem, where instead of b we have this parameter. So we take the diagram found previously and replace b with this ratio. Next, for convenience, we redraw this diagram for b equal ln a over absolute value of k without minus, and we will have the following final diagram, which we will use to solve specific examples. Consider this equation, and it is easy to see that this equation has the simple solution x equal negative 3. If we plug in negative 3 here and here, we will see that the left hand side equal to 8 and the right hand side will be equal to 8. Let's analyze this equation using what we found in this video. We write that a here is equal 1 over 2, k absolute value is 8 over 3, parameter ln a divided over absolute value k is equal negative this number. We look at a diagram which gives us the number of real roots, and we see that this number is greater than negative 1 over e but less than 0, so it is here, and this corresponds to 2 roots. So this equation has 2 roots, of which we had found 1. We use again graphical method to solve the problem till the end. So we plot left hand side and right hand side. This point of intersection of these lines corresponds to negative 3, x1 equal negative 3, and the second point corresponds to root x2, which can be approximately found as a negative this number. So we solved the problem completely. As a next example, we will consider equation. For this equation, a equal 2, absolute value of k equal 8 over 3. This parameter is equal positive value. On the diagram it is to the right from 0, so we conclude that equation has a single real root. Again, we call graphical method. Here is left hand side and right hand sides of this equation. Intersection point gives us the root, which is approximately equal negative this number. In this case, after we found this root, we are sure that there are no other roots of this equation. Our next example is here. A in this case equal 1 over 3. Module k is equal 2. Parameter which we need is equal negative this number, and it is smaller than a negative 1 over e, so it is in this range, and this equation has no roots. On the plot it looks like this, so the curves representing left hand side and right hand side of this equation don't intersect. Very simple solution of this equation. And the final example is this. Here A equal 1 over E, K is negative E, ln A over absolute value K equal negative 1 over E, so it is here. We have single root. Graphically, it looks like this. So our curves intersect in one point, so they are tangent to each other, and it is not easy to find the root by eye, but we can do this analytically. So our equation is here. For A and K, which we have, this parameter is equal 1 over E. So ln Z over Z equal 1 over E. And we can find that Z equal E. Z is K times X from definition, and X equals Z over K, so X equals negative 1. This is a single root of our equation. And now we know location of our point. It is here. The problem is solved. If you like this video, you may want to click like icon, leave a comment and subscribe to the channel.